Hi everyone, Mr. Neighbor here. We're going to finish up one more work problem and then we're going to move on to power. So our problem right now is you are using 50 newtons of force to push an empty cart down the school hall. Your friend who weighs 800 newtons jumps on the cart and wants to be taken for a ride. You push your friend down the hall for 20 meters before being caught up by the principal. How much work did you do pushing your friend on the cart? Let's first diagram what the forces look like before your friend jumps in. So there's a normal force keeping the cart up, there's a gravitational force keeping or pulling the cart down, and there's the 50 newtons that you are pushing with. We're going to neglect air friction right now. Okay, and then we'll assume that the motion is going this way. So velocity's that way. Now let's look at it after your friend jumps on. So after your friend jumps on, the normal force just got a lot bigger because the gravitational force just got a lot bigger. But you pushing probably didn't get any bigger whatsoever. So your force applied, still the same thing. Okay, who knows? It does. You might have started pushing harder, but without friction, which we're neglecting, you don't know. So we assume that you're still pushing with 50 newtons of force. All right, so if we know that, our work being done is always the force parallel times the displacement. So our parallel force is only the 50, and we are going 20 meters. So 5 times 2 would be 10, but really we're timesing 50 by 20, which is going to give us 1,000. So that would be joules. So notice how the friend's weight didn't affect anything because that weight was not in the direction of the motion. That force wasn't. Now we get to power. Power is the rate at which work is done. In other words, how quickly you are doing the work. So the faster the work is done, the more power you're using. So we use the label watts for power, capital W, or horsepower, HP, for units for power. If you want a conversion rate, 1 horsepower is 745.5 watts approximately. That was just calculated by a horse pulling a rope attached to a rock through a pulley. So its force that the horse pulled at was pulling up the rock, and the max force that it pulled became how much power that horse could put out. So that's what we call 1 horsepower. So that one horse, so the story goes, was able to generate 745.5 watts of power from the time it took him to lift that rock a certain distance with a force that was applied. So you can think about this as the equation we use for power. Really, it's an average power because our work done over a certain time, we don't know if that's consistent or not. So that's really an average work that we're looking at. Later on, you'll see that power is also calculated by a change of energy because that's what work is. But you don't need to think about that now. All right, so some practice. A 70 kilogram student in class is lifted in a chair 2 meters off the ground over 5 seconds. So how much work was required to lift the student? So we're looking at work right now, not power. So work, I have to take my force over a distance. So my force would be the force due to gravity and my normal force, or the applied force to lift them. So that applied force would have to match or exceed the gravitational force. Right now, we're going to say the student was lifted at a constant rate up, so it's going to match the force due to gravity. So that means we have to take 70 times 10 meters per second squared to get out our weight force. So 70 times 10 would be 700 newtons. And 2 meters off the ground, which will give us 1,400 joules. If I wanted to do sig figs, I would have to go right here and I would round it down to 1,000 approximately. How much power was used to lift the student? So now I'm going to take my work divided by how long it took me. So my work was actually 1,400 joules, use the precise number, over 5 seconds. So when we divide this, we will get out 280 watts. And sig figs is supposed to go to right there for the 1,400, and the 5 is only 1. So we're going to round this up to be 300 watts approximately. Remember, 1 horsepower is about 750. So this is less than 1 horsepower that the person is doing, which you would probably expect from a human if someone is lifting this person up in a chair. All right, let's move on. While carrying boxes up the stairs, Lucy does 2,500 joules of work in 45 seconds. What is her power output in watts? So this is a very straightforward problem. Power, work divided by time. So 2,500 divided by 45. And when we do that, get out 55.5. And rounding that, we will get out 56 for sig figs and watts as our answer. You exert a vertical force of 72 newtons to lift a box to a height 2 meters in a time of 17 seconds. How much power is used to lift the box? So power is equal to our work. So we have to calculate that right now, which is our force over the displacement. Notice that our force is in the direction of our displacement right now. So that's good. Otherwise, we would have 0. But we do have that. So it's 72 newtons times 2 meters. And this is going to be divided by how much time it takes us, 17 seconds. So we can do all those calculations at once. This gives us 8.47 approximately. 2 is the lowest amount of sig figs, so we have to round there. So it would be 8 watts of power. You lift a book from the floor to a bookshelf 5.4 meters above the ground. How much power is used if the upward force is 15 newtons and you do the work in 2 seconds? So power equals work, which I calculate by taking the force times the distance or displacement divided by my time. I get 40.5. I must round that to 2 sig figs, which would be 40 point and no 0 at the end. I just need to signify I want the 0. Watts, approximately now. Here we have a little bit of a different problem. How much work will it take to move a 10 kilogram mass at an acceleration of 2 meters per second, a distance of 10 meters in 5 seconds? So this problem requires us to use the formulas of force, work, and power all in the correct order. So if we're moving this object, let's assume we're moving it this direction. So we want a net acceleration of 2 meters per second squared. Okay, so that means our net force is going to be calculated by our mass times our net acceleration. So our net force that is being applied is 10 times 2. Is 20 newtons. Next, we have to find the work. So work is your force over a distance. And that distance will be 10 meters, which will give us out 200. And now that is a label of joules. And lastly, our power is going to be work divided by time, which is 5 seconds. That gives us 40 watts of power. Okay, 2 physics students, Ben and Bonnie, are in the weightlifting room. Bonnie lifts the 50 kilogram barbell over her head approximately 0.60 meters 10 times in 1 minute. Ben lifts the 50 kilogram barbell the same distance over his head 10 times in 10 seconds. Which student does the most work? Which student delivers the most power? So let's look at the most work right now first. I see we're almost out of time, so we'll save it for another video.